Welcome, guys. I hope you had a restful Thanksgiving break. Let's review circular motion. This is going to be a 3 video series, and the notes for this video. You should turn in these notes are due 11:59 on Tuesday. All right. So let's go. What is uniform circular motion? Okay. So motion by an object in a circular pattern. All right, in a circular pattern, the patterns ranging from a curve to a full circle. All right. So even if a car has just made a small turn, that curve means they're moving in circular motion. But what makes it uniform circular motion is that they're moving around that curve or full circle at a constant velocity. All right. Uniform circular motion. The car is turning, the object is moving in a circular pattern at a constant velocity. Are we accelerating? Yes, we're accelerating. All right. Yes, we are accelerating. Although I know this is not the question that I just got asked. But yes, we're accelerating. All right. How are we accelerating? Because the object is consistently changing direction. All right. Remember, vectors have a magnitude and direction, and how we define acceleration is the rate of change of velocity. So if the direction is changing, that means the velocity is changing too, and the change of velocity becomes what does it become? It becomes acceleration. So yeah. Okay, so now it's a simple problem here. Just before we get there, just one more note. The acceleration vector always points inward to the center of the circle. All right. So if I look here, let's say I have a car driving around, its acceleration vector will be something like this. This will be acceleration vector. All right. This is where acceleration will point at. Always, no matter where the car is in this circle, its acceleration will always point to the middle, to the center of the circle. All right. So let's see, a car turning a tight corner at a constant speed. Okay, this is the problem here. I'm now here. Problem. We're solving the problem. A car turning a tight corner at a constant speed. All right. We want to know acceleration. Well, centripetal acceleration, which is what this is called, by the way. Centripetal acceleration is given by AC v squared over r. So our velocity is going to be 20 meters per second. Square that over 10 meters per second. All right. That's not squared. Yeah. And so yeah. Our A here now becomes, I'm using a calculator. As you guys know, I'm not very good at mental math. Let's see, decimals. That should be about 40 maybe. I can't really recall. Let's see. 20 squared divided by 20 squared divided by, I don't know why I have meters per second here. Oopsie. I guess I'm rusty as well. All right, 20 meters per second divided by 10. Yeah, it's 40, exactly. 40 meters per second squared. All right? Yeah, so that's our centripetal acceleration. Now, so just to be clear before we move on, so the acceleration, let's see, the name of the acceleration experienced by an object in uniform circular motion is centripetal acceleration. All right? Centripetal acceleration. So the acceleration we're referring to here, that points into the center of the circle, is called centripetal acceleration. All right? Just wanted you to be clear on that. Okay. All right, let's move on. We can analyze the motion of an object undergoing uniform circular motion by looking at its period. I wonder what you guys remember what definition I gave you for period. So, if you don't, well, fortunately, we're here. So, what is a period? So, a period is the time it takes for an object to complete one revolution. All right? See, time it takes for an object to complete one revolution. And you might ask what a revolution is. A revolution is just, it's just one. Think of it as a lap. All right, a lap. All right, an object is an object is starting at some point and finishing at another point. Although a revolution rather is more start at one point and end at that same point, because that's what a revolution. A period is the time it takes for an object to complete one revolution. Now, what about frequency? Here I'm just giving you definitions, and I'm going to show you how they're important or how we can use them to find the velocity. All right, so the frequency, how many times a revolution is completed per second. All right, that's the definition of frequency. How many times a revolution is completed per second. So you see, we have some shortcuts to denote these terms. And these terms are very important. It's important that you know these terms. To say period, we use a capital T, and say frequency, we use F, and the small letter F. So, one more thing to know about these quantities that we've just talked about is their units. So the unit for period is the seconds, and the unit for frequency is 1/seconds. All right, so, and then period and frequency have an important relationship that you should know about. So, relationship between period and frequency. So, our frequency is basically an inverse of the period. All right? That's why the unit of our period is just one, of frequency is 1/second, because it's 1 over period. Yeah? So we can use this formula to interchange between the two. All right, so moving on, we can also use the period and frequency of an object to determine the velocity and acceleration of an object undergoing UCM, uniform circular motion. That's what UCM means, all right? I'm gonna just, uniform circular motion. Okay, so how would we do this? Well, we know the formula for velocity is the delta x over delta t, right? So what's our delta x in this case of uniform circular motion? If we're going in a full circle, our complete displacement will be quantified by the surface area of that circle. So on the surface area of the circle is 2 pi r, all right? And the time taken is going to be the period, delta t. And this is how this is another way, a clever way that will help us in circular motion of finding the velocity of an object undergoing circular motion. You use 2 pi r over t. And this equation has another form. You see, note this is also equal to 2 pi, hold on, apologies. This is also equal to 2 pi rf, all right? And the f really just comes from this being really 2 pi r times 1 over t. It's the same thing mathematically. And 1 over t we saw earlier has a relationship with frequency as such, like right here. So if we know the frequency, if we know the radius of the circle we're traversing, we can find the velocity of an object if we know the period. So yeah, cool. All right, moving on. So how do we handle forces in uniform circular motion? To understand this, we must understand the following, all right? These are the truths, all right? How we're going to handle forces. The truths behind this. So let's get to the truth, right? An object undergoing uniform circular motion is accelerating, all right? I just spent a good chunk of time telling you it's accelerating and showing you how. So I hope you believe me when you say it's accelerating. So Newton 2 tells us when an object is accelerating, we have a net force acting on it, right? So thus, Newton 2 for an object. So yeah, sorry, I'm rushing. So yeah, do you remember earlier in the course I told you that force is proportional to acceleration. So if we're accelerating, then we definitely have a force acting on us. So an object undergoing uniform circular motion is accelerating, right? So why we're having that acceleration is because of the presence of a force. And remember, the acceleration is called centripetal acceleration, and the force that present in this situation is called the centripetal force. The centripetal force, all right? Fc is the centripetal force. Okay. So, checking my notes, making sure I have everything. Yes. Now, the centripetal force is not a new force, all right? Do not put it on your free body diagram. Never do that, guys. Please, do not put the centripetal force on your free body diagram, all right? The force is mainly due to common forces like tension, friction, and the normal force, etc., etc., etc. It literally only tells us these common forces will act towards the center. But we will solve problems using uniform circular motion, basically like any other Newton's 2 problem. Now, instead of saying F equals MA, F equals MAC. And that MAC is the centripetal force. All right? Our application of Newton 2 kind of changes in that way. You know what I'm saying? So, if that confuses you, please come see me during Highlander Advocate. And yeah, we will talk about it. Anyway, so, and some problem solving tips, right? Problem solving tips for problems involving circular motion. When you draw your free body diagram, the object is on a horizontal plane. All right. So when drawing your free body diagram, if the object is on a horizontal plane, like a tabletop. So for example, if you have like let's say a rat running around the floor in a circle, or anything just on a flat surface, or like a coin spinning around on a table, all right, you have to look at it from an edge-on view, all right? Pretend you're looking at it edge-on. And now for your free body diagram, so it will be a regular free body diagram. But our plus x will always point to the center of the circular path. All right. So if I have an object on a rope, and the object is at the end of the rope and it's spinning around, I have a tension there. That tension will point towards the center of the circle that's been made. All right. Then my plus y will be perpendicular to the plus x. All right. So if I have an example problem earlier, and you see what I mean. And most problems are edge on. There are very few where you have to worry about the vertical plane. But yeah, but it's still something good to know about circular motion problems. All right. If the object is in the vertical plane, all right, I'm here now. If the object is in the vertical plane, like a Ferris wheel, for example, the Ferris wheel is in the vertical plane, our plus x, so plus x, I don't know, I have this reversed. For my sanity, I'm going to put that, yeah, our plus x, our plus colors, yeah, awesome. Our plus x, again, always points to the center of the circle. And this time, our plus y is basically all the forces that are tangent, all right? So it points tangent to the circle. So the forces that are acting on the object tangent to the circle is what will go in your plus y when you're in the vertical plane. But in your plus x, your plus x, which is the most common place forces will be acting, will always point, regardless of whether you're in a vertical or horizontal plane, towards the center of the circle. All right? So, now, let me give you something that will, that is true 95% of the time. All right? So true 95% of the time. Not always. All right? But for problems involving uniform circular motion, f of x will always be equal to MAC. F of y will always be equal to 0. Fy, the forces in the y direction will be 0, and the force in the x direction will be MAC. All right? So when you apply your Newton's forces, and just to help you remember, MAC is going to be v squared over r. when you apply your Newton 2 condition to your equations when you're solving these problems, this is what it's what you need to remember. All right? Okay, sorry, I know it's kind of irritating. All right, let's solve a problem. Just to remember how this goes, right? So I have a runner on a circular track. So a runner is a track is a flat surface, right? So I know I have to look at it from an edge-on view. All right. So I know that my x-axis will be the forces that are in that are pointing towards the center of the circle, and my y-axis is a forces perpendicular to that. So I'm looking at my runner like a dot, all right, from the side, basically. So what forces are acting on my runner? Well, he's on a surface, so he has his normal and weight. And then, so that to be a straight line. Pointing inwards is friction. All right? What about friction? Our static friction coefficient. So if I get the forces in the x direction, and that's the next step, forces in the y direction. And remember, here's the question. We have a mass of 75 kgs. The radius is 2.5 meters. And the static friction is 600 newtons, yeah? And we want to find the speed. So we need to do this. So our force in the y direction is n minus w, all right? A normal minus weight, because positive y is there and positive x is there. In our x direction, we only have friction, so static friction. Yeah. Now, we apply the condition. Well, I'm in equilibrium in the y direction, and like the previous section said, f of y is going to be equal to 0. So my normal equals my weight. And then with f of x here, f of x fs, well, here I have an acceleration, right? I have a net force going on. So f of x is going to be equal to mac. So it's going to be fs. What's ac? AC is v squared over r. So h is going to be v squared over r is equal to fs. So now I can just algebraically solve for the speed. So how I need to isolate the v here, and I can simply isolate the v by multiplying both sides by r over m. All right. So if I cancel the r's, yeah, I cancel. Now I'm gonna have v squared is going to be equal to fs r over m, right? So then now I'm gonna just take the square root of both sides. And we see that the formula to get my velocity really is going to be fs r over m. And you have your quantities there. Just plug those in. The physics here is done. We have our equation. So plug those in, and you'll be able to solve your problem. All right, guys. I hope this was a good review. This is part 1. Please watch it, and I hope you understand the content. This is very, very important content.